Okay, welcome back. So I left you with thinking about why is it so difficult to detect planets similar to the Earth around other stars. If we just go back, to this kind of plot, then both of the main techniques here, the radial velocity technique and the transit technique, preferentially detect sort of massive or bigger stars that are closer in to their host star. So if you've got a massive star, a massive planet close to the star, it's going to cause the star to wobble more, so it's easier to detect the radial velocity variations. If you've got bigger, larger radius planet, then obviously you get a bigger dip for the transit. And for both techniques, you know, if you want to find planets that are way out a long way from their star, their period is long, so you just have to wait a long time before you can pick them up. Okay, so here's the period of Jupiter at about 3,000 days, so about 12 years, I think, period of Jupiter. So, you know, if you're waiting 12 years for your transit to repeat, then that's quite a long, quite a big ask. So even for the Earth, you know, you have to wait a year for that to repeat. And so they're getting close, but not close enough yet. So there are other missions up there at the moment. TESS is doing something similar. The TESS satellite also looking for transits. And there are other experiments on the ground which can run for much longer and try and pick them up. Okay, so now we want to see what the role radio astronomy can play in all of this. Well, as we shall see, where radio comes in is returning to the topic of the previous lecture, where basically the solar wind that comes out from the host star, so I'm calling it a solar wind, obviously, even though it's not the sun in this case, but you know, the streams of charged particles that any kind of active star, so we think all stars, or most stars, will have that kind of energetic flaring activity. So you get this continual stream of fast charged particles flying out through into the neighborhood where the planets are. And if there are any planets that have a magnetic field, then those charged particles will interact with that planetary magnetic field and give rise to radio emission. Okay, so let's explore that by first of all looking at radio emission from planets in our own solar system. So just a reminder, you know, this is just a cartoon really showing you these kind of ejections of charged particles coming out from the active sun. But like I say, most stars similar to sun and lower mass will have exactly the same kind of behavior because they are all convective stars and generate their own magnetic fields. And then when that charged plasma interacts with a planet with a magnetic field, some of that charged particles will start to spiral down the magnetic poles of the planet. So on the Earth, that manifests itself as so-called aurorae, the northern lights and the southern lights at the north magnetic pole and the south magnetic pole. So when the charged particles enter the Earth's atmosphere, they cause fluorescence, and so you get these strange patterns, but only if you live in very northern or very southern latitudes. I've never seen them myself. Just to give you another view, this is a little movie of what the aurora on the Earth looked like from space. So imaged in the far ultraviolet from a satellite. And so you can see when these solar storms of particles hit the Earth, then you get this ring of bright emission all the way around the Earth's magnetic pole. Let's just have a look at that again. So this is the Earth's magnetic pole, and you can see this ring, which is where the magnetic field lines are channeling the particles down onto the magnetic pole of the planet. And it's not just the Earth in the solar system that exhibits these aurorae. So these are Hubble Space Telescope pictures, enhanced to show that the gas giant planets, Jupiter and Saturn, also have these aurorae. Okay, so you can see very similar to what we get on the Earth. You get a ring of emission here at the north and south pole, some magnetic pole of Jupiter, and the same thing on Saturn. Okay, so these streams of magnetic charged particles are going all the way out through the solar system. Once they've left the sun, they're not going to stop. So obviously this is also telling us that Jupiter and Saturn are also have magnetic fields. And this is a little movie of the aurora on Jupiter. So you can see an awful lot of patterns in here. If I just stop that for a second, there are particular trails here, but you can see other ones here. And interestingly, these are actually associated with the moons of Jupiter, especially Io. So Io leaves behind it in its wake a trail of plasma, and that gets sort of electrically connected via the magnetic fields to Jupiter itself. And so you can kind of see the imprint of the moons of Jupiter and how they orbit around in this time sequence of auroral patterns on Jupiter. Let's just show that again. So again, these spots are, in a sense, reflections of where the magnetic connection from the moon goes down onto the magnetic pole of Jupiter. So, so what frequencies are we talking about here? Well, sort of planetary radio emission is very much at the low frequency, in the realm of low frequency radio astronomy. Very low frequency, really. So here is a spectrum of the sort of typical emission from Jupiter. And you can see, just looking at the solid line here for the moment, then it's extremely strong. Okay. So Jupiter is a very strong radio emitter, at least, as viewed from Earth, but only up to about 40 megahertz. Okay, so once you get to 40 megahertz, there's a massive cutoff in the spectrum, and above that, then the emission is pretty weak. Okay, so it's down here in the sort of tens of megahertz frequency range where where Jupiter's radio emission is extremely strong. And in a sort of similar style, this is another of these dynamic spectra. Okay, you get an awful lot of structure. You tend to get these bursts. Okay, so when the charged particles, when a front of charged particles comes in, you'll get a burst of radio emission for a short time. A lot of structure in frequency and time. So you can see that on this dynamic spectrum here. So again, in this sort of 30 to 40 megahertz range, and just lasting less than an hour or so for one of these bursts of strong radio emission. And that emission will also be very circularly polarized. So again, this is due to particles coming in along field lines, and they will start to spiral along the field lines as they come down onto the magnetic pole of Jupiter. And it's that spiraling motion that gives rise to the circular polarization of the emitted radio waves. So you can now hopefully begin to see why radio studies might be rather interesting, because if you ask the question, why does a planet have a magnetic field? And then it immediately starts to tell you about the internal structure of the planet. Okay. So we can diagnose things about the inside of a planet by studying the magnetic field that surrounds it. Okay. So the only reason the Earth has a magnetic field is because it has a liquid iron core. Okay. So prerequisites for a planet having a magnetic field is that you've got some kind of conducting medium that is basically liquid and can move. Okay. And then you need, in order to generate the sort of dynamo effect, you need a combination of rotation and convection. So you also need a sort of a big heat gradient in your planet. So it must be much hotter in the center than it is further out. Okay. So the Earth has all of those ingredients. So you've got the liquid iron core. You've got a solid core in the middle, but then you've got liquid iron all around it. And the Earth is rotating, and there's convection in here. So that gives rise to the Earth's magnetic field. Now, of course, the Earth is a rocky planet, right? I mean, that's why it's got iron in the middle of it. But Jupiter is a gas giant, right? It's most of the planet is made up of hydrogen gas. So how does that conduct? Okay, well, the hydrogen, when it's under extreme pressure down here in the center of Jupiter, turns into a peculiar form that is referred to as liquid metallic hydrogen. And so the electrons become free and able to move through this high pressure on the hydrogen, and that enables it to conduct. And Jupiter is also a fast rotating planet. I mean, it rotates about every 10 hours. It's really quite faster than the Earth, and it's a big body. So that's a lot of energy. And again, you know, it's going to be hotter in the middle than it is on the outside. So it's got all the ingredients for generating a very strong magnetic field. And the same for the other gas giants, Saturn, Neptune, and Uranus. They all have magnetic fields for the same reason. So it looks like we have the potential to start diagnosing the interior structure of planets orbiting around other stars if we can tap into understanding this and detecting this radio emission. So we'll come back to the more details on that in a moment. But for now, let's have another short break. And something to think about during this break might be the planet Mars in our solar system. It's a rocky planet, a bit further out than the Earth, and quite a bit smaller than the Earth, but no longer has a magnetic field. We think it did in the past, but it doesn't now. So have a little think about maybe why Mars no longer has a magnetic field. We'll come back in a sec.